Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to Learning by Solving Problems, Session 4 on Carbohydrates. The relative configurations of the stereoisomers of tartaric acid were established by the following synthesis. Number 1, D plus glyceraldehyde with hydrogen cyanide gave compounds A and B, separated from each other. Step 2, hydrolysis of A and B using aqueous barium hydroxide gave compounds C and D respectively. So A gave C, B gave D. The third is oxidation, nitric acid oxidation of C and D gave negative tartaric acid and mesotartaric acid respectively. You know the absolute configuration of D plus glyceraldehyde. The OH, right. D plus glyceraldehyde. So show the absolute configuration of A, B, C, and D. Show the absolute configuration of the three stereoisomers of tartaric acid plus tartaric acid, negative tartaric acid, and mesotartaric acid. Well, we have here D plus glyceraldehyde. When we treat it with HCN, potassium cyanide, we get a mixture of the extended cyanohydrin, one more carbon, either the OH right, or we get it on the left. So it's mixture, diastereomers, which we can separate. Okay? He mentioned that separated. Then when we treat each of them with barium hydroxide, we get the cyanide group hydrolyzed to carboxylate in basic medium. Well, either this one, for the other compound, we get the OH to the left. Here is right. Well, treating that each of them with nitric acid, you oxidize the primary alcohol. So we get meso structure, since we have here plane of symmetry. And we get, as he mentioned, the negative tartaric. So the negative tartaric should be here, right, and this one on the left. Well, we go backward. We have here a plane of symmetry. This comes from the carboxylate, this compound, and this one will come from the cyano. So this one should be D, and this one should be B. Here, the negative tartaric acid will come from C, and C is coming from A. This is the mesostructure of tartaric, and this one is the negative tartaric. Well, here's the mesotartaric, should be R and S. The negative tartaric, SS, and the positive will be enantiomer of the negative, so this will be R and R. Just to remind you how we do that, let's assign the configuration around this carbon. we can do double two group arrangement. So we get the H to replace COH and the other way around. Okay, and then when we do the second transformation, we will get to the same compound, same configuration. So now we get the OH in place of COH, COH and OH. Now the lowest atom will be hydrogen in the back. Here is one because we have oxygen. Here priority or seniority number 2, COOO. So this is number 2 and this will be number 3. So the priority is going 1, 2, 3, counterclockwise or anti-clockwise. This means that it is S. Yes, it's S2S, and we will find the 3 is S2. Okay? To revise the carbohydrate part of this chapter, let's cover this question. Predict the products obtained when D-galactose reacts with each reagent. Bromine and water, sodium hydroxide and water, methanol and acid, ammoniacal silver nitrate, Tolling reagent, hydrogen nickel, excess acetic anhydride in pyridine, excess methyl iodide silver oxide, sodium borohydride, bromine water, then hydrogen peroxide and iron-free sulfate, hydrogen cyanide, then acidification, this sodium amalgam, excess periodic acid. Well, this is the structure of galactose, open structure and cyclic structure. So in tautomeric forms. Open structure, cyclic structure. D galactose with bromine water, oxidation of the aldehydic group to carboxylic acid group, so we get galactonic acid. Galactonic acid. When we treat galactose with sodium hydroxide water, what we do actually is isomerization, as we covered in lecture 11, epimerization at carbon 2 and the ene-diol rearrangement. So we get here epimerization, we get the OH and the other way around. And we get the ketonic. Okay, so we get D-tallose and D-tagatose. When we treat D-galactose with methanol in acidic medium, we methylate the anomeric OH. It will be OCH3. And we get the glycoside, methyl glycoside. Here, the compound will be methyl D-galactopyranoside. Here is alpha and beta mixture, O-methyl, and here is OH, 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 OH. When we treat D-galactose with ammoniacal silver nitrate tolling reagent, the aldehyde will be oxidized and silver one will be reduced, oxidation reduction reaction, and we get deposit of silver mirror and the formation of galactanoid. D-galactose catalytic hydrogenation using hydrogen nickel, we will reduce the aldehyde C double bond O to OH and formation of primary alcohol. That will be galactitol. When we treat the D-galactose with excess acetic anhydride, we acetylate all the OHs 1, 2, 3, 4, and 5, and we get 1, 2, 3, 4, 6 beta O-acetyl D-galactopyranose. Okay, again here is alpha and beta mixture. When we treat D-galactose with methyl iodide silver oxide, we methylate all the OHs with the formation of 1, 2, 3, 4, 6 beta-O-methyl D-galactopyranose. Treating D-galactose with sodium borohydride, again we reduce the aldehyde to primary alcohol and we get D-galactitol. Treating the D-galactose with bromine water, we get this COOH. Then when we treat it with hydrogen peroxide, iron 3 sulfate, we decarboxylate and the formation of this carbon will be the aldehyde. Go and see lecture 14 for that and the reaction mechanism. When we have the D-galactose, we applied hydrogen cyanide, then hydrolysis, and then reduce with sodium amalgam. We extend actually from C6 D-galactose to 2,7 heptosis. Of course, when we add the hydrogen cyanide on this carbon, on the carbonyl, we increased one carbon, cyanohydrogen formation on the first step, and the OH will be either right or left, and then the cyanide upon hydrolysis will give carboxylic acid, followed by lactonization reduction with sodium amalgam to be an aldehyde. Again, check lecture 14. Finally, when we react the D-galactose with excess periodic acid, we oxidize on this carbon-carbon bond, carbon-carbon bond, OH-OH between the OHs. So we consume 1, 2, 3, 4, 5 periodic acid per each molecule of the D-galactose. The aldehyde will be formic, this carbon will be formic, 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 formic acid, and the last one will be formaldehyde. So we get 5 molecule of formic acid and 1 molecule of formaldehyde for each molecule of D-galactose. Check lecture 12 and enjoy it. Finally, let's cover this one. What is Molisch test? You will find that in the lab course. Molisch test is a test for carbohydrate or compounds which can be dehydrated to furfural furane 2 carbaldehyde or furfural derivatives in the presence of concentrated sulfuric acid. The Molisch reagent is actually alpha naphthol in ethanol solution. So when we get D-glucose as an example, we add sulfuric acid, we dehydrate this molecule to 5-hydroxymethyl furane 2 carbaldehyde or 2-hydroxymethyl furfural. Well, when we add this aldehyde to Molisch reagent, one molecule of this furfural with two equivalent molecules of the alpha naphthol will form a purple viral color complex at the interface of the acid and the test layer. So we get these species will oxidize -2 electrons and deprotonate to form a purple color dye. If the carbohydrate is poly or disaccharides or even glycoprotein or glycolipids, the acid first hydrolyzes it into component monosaccharides, which get dehydrated to form furfural and then will give a positive test, which is a purple color dyes ring at the interface of the acid and the test layer. See you next session.